Hi, I'm Alan, and that's me on the screen. I work at Daghouse. I'm a software developer, software engineer, building Web3.storage. It's this nice thing. So I'd like to start with what Web3.storage is. It's the easiest way to onboard data to the decentralized web, and that means IPFS and Filecoin. And this looks like a serious talk from that slide, but it is in fact not. Half of these things on the screen right now don't exist, but they're kind of cool. I'm going to tell you what I mean by them, but they kind of relate to cool features of Web3.storage that I'm interested to talk about. So let's do it. So I'm going to start with the past and move into the future from there, I guess. So 2021, that's where it all began. Web3.storage spun out of a project that was called NFT.storage. And it was kind of like this, this amazing thing that happened. We built NFT.storage really quickly, and it was for just helping onboard data into Filecoin. But people started using it loads, and you can see from the testimonials that people were kind of jazzed about it, and so it kind of took off. It got big, and then weird things happened, like other people started talking about it that I don't even know, and then there's like swag and stuff that happened, including like bum bags, or what do you call? I don't know. Anyway, and then like whole buildings get branded as NFT storage, and then stuff like this happens, and I was sat there sort of just typing away, thinking like, what is going on? And then like NFT storage is in the airport, and then whole trains are branded NFT storage. And then this guy on the internet sings a song about NFT storage. What the heck? What is going on? So that was 2021, a bit of a wild time. And so basically NFT storage was built in 2 weeks. It was a tool to be used by an NFT hackathon. And the idea was it would just allow them to store NFTs on IPFS and Filecoin. Filecoin had just launched at the time, and it was looking to onboard data quickly and also fix the bugs. It wasn't always easy to onboard or offboard data onto Filecoin at that time. So anyway, enough about NFT.storage. This is the first iteration of Web3.storage, which kind of came about as like you know what, we've got this cool NFT storage thing for NFTs, but what if there was more like a more generic kind of for every type of data solution? And so Web3.storage came about. The big thing about Web3.storage was that it was a major step towards Web3 from NFT storage, which was very kind of Web 2 oriented sort of service. And instead of uploading files directly to the service, we content addressed them on the client side. And we started accepting car files. So when you import stuff into IPFS, it becomes a DAG, it has a CID, and if you want to send that DAG somewhere, then typically you'd kind of pack it up into a car file. And so cars were our primary upload means at that time. And our architecture at the time was like, I mean, it says Fauna there, but we moved from Fauna to a big giant Postgres. We were using IPFS cluster at the time, and Cloudflare workers to accept uploads. So that's kind of fun. Cool. And then we kind of got into this, what I'm calling the steady state, except actually, it wasn't very steady. We had rainbow graphs. Rainbow graphs look nice. They are not nice. Ideally, you want your graphs to be high or low, depending on if you want things to be high or low. You don't want them to be jazzing around everywhere. So rainbow graphs like this make for good screensavers, but actually our service was struggling. our IPFS cluster instance grew to over 50 nodes. And what we were finding, as you see in the top left there, is that any given node in the cluster was receiving a lot of writes because there were write targets, but there were also read targets as well. And also because of DHT stuff that needs to happen, they were re-providing to the DHT, and sometimes they had, well, we had to learn this, but don't let your IPFS nodes get too big, too full of data, because at some point, the list of things that it needs to send to the DHT to keep saying that I have this thing gets too big, and they sort of expire before they get to the front of the queue, and there's just too many things to get through, and the node basically gets super busy. A lot of our nodes were like that hot, tired face there. So anyway, those times. And then, so the steady state came around when Elastic IPFS came around. It really saved us from that. Elastic IPFS is a cloud-native IPFS implementation, and the basis of it is separating those read and write pipelines to achieve a much larger scale. And it also leans into car files at rest. So what we did was we started to write car files to buckets and just make a big index of like the block indexes within cars. And then our bit swap implementation in Elastic IPFS just reads, it uses HTTP range requests to read specific blocks out of cars. And you can do kind of fun stuff with that. Like if you've got two blocks that are close together, you can make one request with both blocks in it and stuff like that. So that's cool. And so with Elastic IPFS, we were eventually able to retire our IPFS cluster. I said it was like over 50 nodes at the end of it, but that saved us many thousands of dollars every month, which was rad. It's not to say that IPFS cluster isn't any good or at scale. We had tremendous scale with IPFS cluster, but we needed to move on from there at a certain point. And then this thing called Freeway came along, and Freeway was a kind of speed optimization and cost-saving exercise. So Freeway is kind of a no database IPFS gateway where Elastic IPFS has a database which stores like the block offsets in a database. Freeway, the idea was like we index the car, but we store the index as a file. The index is just a carv2 file, carv2 index file. And we read from that index, and we have symlinks set up as well, which sort of say this interesting CID, like a root of a file or root of a whole DAG, is in these car files, so you can fetch it out of there. So you can read the index and then get the blocks out. So Freeway basically just serves data directly from car files at rest, rather than going over BitSwap, and that's kind of faster and saved us a lot of egress from BitSwap. Cool. Okay, so we spent almost all my time on the past. So anyway, things were better now. The fires were less, and we still had some centralized infra, though. We had centralized upload targets. We would be accepting data through Cloudflare workers. You could only send it to us. We had an opaque data aggregation pipeline. Like you would send us stuff, and at some point in the future, it would become aggregated together into a bigger chunk of data that would go into a Filecoin deal. And at some point in the future, you'd get a Filecoin deal, but you had no idea like what was happening between the point you sent it to us and that. We also had unverifiable operations. So you literally just sent us stuff. There was no proof of who had stored what, aside from our giant Postgres, which you could look at, and I guess, but big giant Postgres is probably not what we want, at least for this crowd. And so, yeah, we weren't able to take advantage of content addressing. The beauty of content addressing is that if you're content addressing, you actually don't need to send the data if someone's already got that hash. And so what we had to do is that you would always have to send a car to us. You just always had to do that. And so that's not good. So we're leaning into UCANs to solve a lot of these problems. UCANs are user-controlled authorization networks, and they use public key cryptography. So you sign a UCAN, and they have this concept of capabilities and delegations, which is really cool. So some examples of capabilities that we, or abilities that we have in our system, are StoreAdd for storing some data. You can offer a piece to Filecoin for aggregation and deals, and you can list uploads and stuff like that. So anyway, you can delegate those capabilities to other people, and they can delegate on to other people as well. And in a UCAN, the delegation chain is included. So every UCAN that gets sent around has this full chain of authority like baked in, which is great. So there's no like central authorization server. There doesn't need to be, because of the delegation chain that's baked into UCANs. But there is now verifiability for operations, so you can see when you've been when you've sent something and who's done what. And so this is kind of what I mean by that title of the talk, which is Zero Knowledge Auth. You don't need to have any knowledge of of the authorization list or whatever, because it's all baked into the UCAN, and that's kind of what they provide, which is really interesting, I think. So basically, it's all cute Disney characters in this new version. We built this UCAN RPC library called UCANto, and that allows you to make invocations with UCAN. So it's a way of using those capabilities you've been delegated to get tasks done. And then you get receipts from those UCAN invocations, and they communicate the results from tasks. And the receipts kind of can look a little bit like this. There's more to them than this, but I've super simplified it. But basically, it's a result or a CID of a task that will complete in the future, and you can check in on that task at a later date and see if it has happened. And so we have this data aggregation pipeline. You can kind of see how, if we've sent a signed UCAN to say invocation to say I want to store this or put this piece in Filecoin, and we might get a future task that's like it's going to be aggregated. Check that later, and then you could check in on that and get a receipt for the aggregation, so you can see which bigger aggregate piece your piece has been aggregated in, and that will include like an inclusion proof, so you can pick out the exact thing that you're storing. But you can follow it through all the way. So once you've got that aggregate, you'll then get a future task, which is like this is going to make it into a Filecoin deal, and you can check in on that with the aggregate and receive the deal information. So what is called like a data aggregation proof, where you have like the deal ID plus the inclusion proof for your piece within the bigger piece. So yeah, it's rad, because we've now got this amazingly verifiable system that you can follow through that we just never had before. So that's really fun. And also thanks to the UCAN receipts is that we now have these this I guess capability of being able to have decentralized upload targets. So yeah, what you do with a StoreAdd invocation in our system is you say, I'd like to store this car file, and with car files we actually content address them as well, so they get their own CID. So you say, I want to store this CID, this car file, on Filecoin, on hot storage, wherever, and you get back a receipt that says, okay, this is where you put it, and so that URL is currently like just a bucket that you can put stuff to, but in the future that could be some other target. That could be like a Saturn node, for example, or it could be a storage provider themselves. We also spec out all of our UCAN systems, so there's this hope that people could implement some of the spec and become targets for for posting aggregates to. They could aggregate data together, or they could receive aggregates for putting in deals. But and so with the decentralized upload targets, this gives us an opportunity to say, we've already got this car, it's already in a deal. Like, you don't need to send this to us. So when you do a store ad, you get back a really quick response that says, that is done, you don't need to do anything. And this is from the talk title again, what I call infinite compression. Is not really that, but in all seriousness, content addressing is rad, right? Imagine just being able to do that. And if you want to resume, if you've got a big video, say, and what we do is we shard it up into many car files. You could go through, you could get halfway through and resume. And basically, if you want to resume, you'll get like a bunch of things saying, we've got these cars, and you can then continue where you were left off because maybe you got on an airplane or your internet dropped out or whatever. So yeah, very cool. And so we launched the UCAN offering of Web3.storage literally a couple of days ago. So all of these benefits have just been realized. Now, the future is unwritten. That's why this slide is relatively blank. And also, I didn't have much time. So, but what we would like to do in the future is we'd actually like to decentralize that upload target. We'd like to maybe put it in like hot storage for Saturn, perhaps. I don't know exactly how it would work, but that's the idea. We've got that opportunity now. We also run our own gateways. We'd love to sort of offload some of that responsibility onto Saturn. So it would be cool to work with them to realize that opportunity. And there's a whole bunch of other stuff, like we store some metadata in the database. It would be really nice if actually all user data was just a DAG that they stored in their space, including like all the indexes and things that we do. Yeah, there's this other awesome thing where we'd love to do like what we call dilution pricing, which is like if you're storing something and someone else is storing something as well, then maybe you halve the cost of storing it. And like the more people, the less you pay because it's not actually costing us any more money to store. So anyway, the future is unwritten and I am over time by 2 minutes, but I'm Alan. I've been working at DAG House for a long time now. We are having fun and making awesome things. Web3.storage is good fun. You should check it out because it has changed significantly into this awesome new system now, and I'm really proud of it. So come talk to me after if you want to talk about that sort of thing. Come to the workshop later where you can, oh yeah, the workshop, right? You can actually use it. There's a workshop later at 4. It's billed as like a joint Saturn Web3 storage workshop, and you can actually use the upload service at the workshop, and it's guaranteed fun. So that's our house in the Merkle forest. Thank you very much.